Hi, Dr. Memori again. I am going to perform the last experiment for 1045 lab, and that is the Beer's law. Let me share the file for Beer's law, so we could go over some theory for the experiment. Basically, the method is calorimetric. And what we are trying to do, we are trying to find concentration for unknown solution based on the intensity of the color that it produces. So the product or the reactant or the active ingredient or what we're trying to measure the concentration, it should cause formation of a color that has the maximum absorbance at a certain wavelength. Different color, they have the maximum absorbance at the best wavelength, which is known as the lambda max. So that lambda max is already determined for this experiment. The instrument looks like this machine, and I have the equipment, the instrument live right here. We are going to use it, set it up, and use it. If we look at the second page of this experiment, so basically it's a titration method or measurement of the measurement for concentration. So what we are going to do at this point, we are going to just look at the formula. The formula that we are looking at for that follows the Beer's law. It shows absorption of the light by the solution. It depends on some variables. We can keep the value or the pathway for the light, which is the 1 centimeter here. That depends on the cuvette that we are using. So if we are using this type of cuvette, it's going to be kept as 1 centimeter there. So it's a constant number. This is a coefficient. The epsilon is a coefficient, which is again a constant number. The C is the concentration of the solution. So basically, concentration of the solution is directly related to the absorption. The higher the concentration, the higher the absorption. That is the idea that we are going to use. And in order to use this technique, we are going to first build a calibration curve. The calibration curve is going to be built based on concentration, known concentration of our solution. So basically, we know already, we have few, we make or prepare 3, 4, 5, the more the better, but we are going to make at least like 4 of them. So we have at least like 4-point graphs, so the more number of points, probably better. We are going to make our solution different concentration. We are going to use the machine and determine the absorption, measure either transmittance or the absorption. When we have these values, we are going to then plot the graph. The graph that we plot for absorption versus concentration is known as the calibration curve. Let's say we have an unknown compound. That unknown compound, if it's going to have like 0.42 absorption, then we extrapolate this a line, we draw a perpendicular line from the absorption to cross the best fitted line or the calibration curve, and then from that we are going to draw a perpendicular line to concentration line, the x values, and we find the value for concentration of the unknown solution. So that is more of the theory. Again, the purpose of the experiment, by performing this experiment, is to be able to teach this class remotely. So I'm not teaching the class, I'm just performing the experiment, but I have to explain what I'm doing. And if it's me or another professor teaching the class, is going to explain more about the theory and ask you how to, would set up expectation. When I perform this experiment, I'm going to perform it in a way that you would record your data. You record your data values, and based on the data value, you are going to be able to finish up and complete your data sheet to turn in as an assignment, because you cannot be here to do the experiment. I'm doing this experiment so you can have your data values in order to finish your or complete your data sheet to turn in as assignment. So we are going to perform the experiment, and I'm going to stop sharing this document. I would use my lab manual in order to follow the procedure. Let's go ahead and start with the experiment. Okay. So based on the procedure, that at this point, definitely you have your lab manual, purchase from vital source, and we are looking at the procedure. It says label dry Erlenmeyer flask A to E. I have already five Erlenmeyer flasks here. They must be dry because we don't want to change the volume. Volume has to be accurately measured. And one of the best devices in the lab to measure the volume accurately is burette or pipette, but burette is more practical because we could use different increments of the volume. So we are going to follow the table that is provided in the procedure to fill up the flasks, following the procedure. So we are going to use the burette for each one of them, following the table to the flask A. Flask A is going to serve as a blank. Why are we using blank? Because we want to make sure that for better purpose of the use of the instrument, we want to make sure that we have a reference to refer to as the zero absorption, because this is not going to have the active ingredient, so it's not going to have basically iron 3+. So whatever the measurement for this is going to be zero absorption. Ideally, or the machine needs to be calibrated for zero absorption. Then we make the other 4 solutions following the table. So we're going to calibrate for reading of those 3. Instrument is on already. The wavelength, I set it up. I'm going to show you because it tells you in the procedure, so I want you to know what is done and how it's going to be performed, this part of the experiment. We can change the nanometers, we can increase or decrease, and it's saying that set it up at 480. I just set it up at 480, but I'm showing how to go up and down here to make it 480. And then it says ATC, concentration, absorption, or transmittance button, to use this to change it to the %T. So if you press it, it can go to concentration, it can go to absorption, or the %T, and we are keeping at the %T following the procedure. So next step, we are going to add the 5 milliliter of the KSCN to the flask B for 5 minutes worth for 5 minutes. Okay, so we are going to set up. Do not add the KSCN. So everything needs to be added to each flask using the table, and for A, blank. The only item that we are not going to add is the potassium cyanide. Why are we adding the potassium cyanide? Because if we add the potassium cyanide, it's going to start, the reaction is going to start, and since we have to time it for 5 minutes, then if we start and I try to fill up all 5 flasks here, it's going to take a lot more than the 5 minutes, and it's not going to be proper comparison of the concentration, because each of these flasks needs to stay 5 minutes before we can measure. So let me follow the procedure. Watch me as I'm following the procedure. So we are going to add 0 milliliters to A, 0 milliliter of standard, me just set up this at a good number so I can, when I'm reading, so this is at exactly, it has to be set exactly at a number. Okay. So for A, I don't need any iron, so I'm adding nitric acid. Why should I add nitric acid and how much? 5 milliliters of nitric acid. When you add nitric acid, let's say you have iron, that iron could be like iron, it could be iron 2 plus, it could be iron 3 plus. So what it does, when you add nitric acid, what it does is going to make all iron change to iron 3 plus. So when you are measuring iron 3 plus. So you want to make sure that the iron is in iron 3 plus format. I'm going from 29 to 34 to add the 5 milliliters. 1, 2, 3, and 4. It's better to hold white background or something behind it so you can easily. Okay. Exactly. 5 milliliters of KSM added, and then 0 of that. Okay. So I have my solution A prepared. B, 1 milliliter of the iron. So I'm going to add 1 milliliter of iron. Okay. 1 milliliter of iron. This will be 4 milliliters of nitric acid. So I go from 34 to 38. Four moles of nitric acid. And KSM, we have to add it later. So A and B ready. C, 2 milliliter of the iron. I'm going from 19 to 21 now. Iron added. 3 milliliters of nitric acid. Go from 38 to 41. Okay. Then we add, C is ready. D, 3 milliliters of the 3 milliliters. So I go from 21 to 24 of iron. Three milliliters of iron and 2 milliliters of the nitric acid. 41 to 43. 41 to 43. Okay. E, 4 milliliters of iron, going from 24 to 28. 24 to 28. Four milliliters and 1 milliliter of nitric acid. And 1 milligram lactic acid going from 43 to 44. The total volume must be the same, so for all of them it should add up to 10 milliliter total. So that's why we change this, the increments, how it's done. So the flasks are ready with exceptions to KSCN. KSCN we're not adding because as soon as we add, we have to time it for 5 minutes. Okay. So going to add one, it's 157. I'm adding the KSCN 5 milliliters. Instead at specific number to make it easy. I'm going to go around. Set at 15. Go to 20. Okay, 20. We have 5 minutes for B to be ready. Just setting up for 5 minutes. And while we are waiting for the 5 minutes, we should be able to work with sample A, following the procedure. Okay. Okay. We are going to fill up cuvette with the solution A. It asks partner, but unfortunately I don't have one. So I'm going to have to manage to do it all myself, all by myself. Okay. Place it and press the 100%. So we are going to calibrate the machine with solution A because solution A had no either. So if this machine is going to read the solution A with 100%, that means it's calibrating the machine that for others is going to read the change in color, how much color or what is the intensity of the color that has been generated, and based on that, the absorption is going to be higher. The more color, the higher the absorption of the light, so smaller value for percent transmittance. So we're done with A. We're waiting for B, 57, and since it's 57, I have to wait for 203. 203, I have 3 minutes time, and I think if I write these down, I can manage to do 2 or 3 hours. So for A, I have 100%. For B, I started at 157. I have to wait to 2 or 3. For C, I'm going to start at 2. I have to wait to 205. So let me start with the C. I have my solution for C also set up at 2 o'clock. I have to wait for 2:05. I can test my solution C. This is just being more efficient. I could have just stayed with the B, finish 5 minutes, and then start with the C, wait 5 minutes. But this way, if I can keep track of my numbers and the waiting time, the time lapse, I can manage to. I have 2 more minutes. I'm not gonna be able to do that. I probably can start at 2:02 for sample D. 2 202 going to 207, because if I do back to back, if I start the other one at like 201, 1 minute time is not going to be enough for me to test B and then be ready for C. But if it's 2 minutes, I think I can do it. It doesn't take that long. So 2 minutes it should be. So I'm taking that sample A already out and waiting for sample B. Okay, 202, I'm going to start with my sample D started at 202. My sample B is going in at 203. I have to get ready to put my sample into test tube. It's actually not test tube, it's called a cuvette. It has a special mark on it. It's a special brand of a test tube. And these cuvettes, they are special glass that doesn't have absorption of the light, and they are better quality of the test tubes. Okay, 203. I need to read the sample B. When I read the sample B, I record the number 91.7%. Okay, 91.7%. And okay, it doesn't change. Good. Done with sample B. My sample C should go in at 205. I have 2 minutes. I can start with my sample E. I'm going to start at 204. So 204, my sample E. Sample E should go in at 209. Now, my sample C should go in at 205. So I have to be ready with my sample C as soon as the clock ticks the 205. I can place my sample C in. Just have to make sure that it's clean because I touched it. So we are using Chem Wipe to clean, and Chem Wipe is just a special type of paper. It's not, since you're not here, I just have to show you what it's talking about when you say Chem Wipe. So 205 sample C is going in and the flask is going out. 85.3. 85.3%. Okay. My sample D is going in at 207. So I just have to wait now because I don't have other standards. I'm just going to look further to see what else I need to. Okay. 207 D is going in. So I'm going to start getting ready. If the sample is in the test tube or is in the flask, it should have the same time for intensity of the color, basically. So it's okay to pour it into test tube and wait until it's 207. As long as I don't read it and I wait until 207, it should be fine if it's in the flask or is in the cuvette. Okay, it's 207, so I can read my next sample. Two oh seven. B is 77.3%. 77.3%. Perfect. Take it out and wait until 209 for my sample to be ready. Sample D is done. Sample E is next one, and that's the time that I need for that is a 209, 5 minutes time. So I'm going to make my unknown. I have 1 minute time. I'm trying to see if I can make my unknown A. Unknown A. So let me know if it's 209. I have to get ready for this, okay? 209, I have to place my sample in. I cannot wait. So for 209, it's 5 milliliters of each. Unknown A. I'm looking at the time, not you guys. So I don't wear a watch, so I check the time from the computer. 209. Let me finish my calibration first. Okay, sample E is ready. Time is 209. Place the sample in, and we record the number. 74.8%. 74.7% because it changed, and then from 74.7 it stayed constant. Okay. Now, going to make my unknown A. For unknown A, we need the 5 milliliters of the unknown solution. So, going to start from. Okay, watching me? Okay. Going to start from 22 and go down to 27. Okay. My cyanide have 35, going to down to 40. We look at the time, it's 2:10. 35 to 40. Okay. I have to wait for 5 minutes until 2:15 in order to make the unknown. So unknown A, I like to write it down so I can get the 2:10 to 15. Unknown B. Get unknown B. It looks like there's high concentration of the iron in the unknown A. I'm not 100% sure what the concentration is because I didn't look for the unknown, but whatever it is, we are following the procedure correctly and we're going to write what we see. My unknown A and B ready. Unknown A, I started at 210 and I have to wait to 215 to use the unknown. For unknown B, 213 to 218. Which one has higher concentration? So this should have higher absorption also. A has higher concentration, B has lower concentration. Looks like A is out of the range of our calibration also. It's too dark compared to all the solutions that we had already. So in your calibration curve, it might be like outline or out of higher than every other sample that you had. The formula to convert the percent T that we are measuring into absorption is in step 6 of the procedure. Okay, A equals log of 100 divided by percent T. That's the one that you are using for all of these values. The percent T that I'm going to report to you to convert it first before you plot your calibration curve. Okay, 215, and I'm going to use my unknown A. .3% T. And for unknown B, I have to wait to 218, 2 more minutes. So when you have your calibration curve, you have to look for the concentration and use the calibration curve in order to find the concentration for the unknown A or unknown. The instrument, if it's calibrated today, it needs to be calibrated next day. So all the solutions that are measuring for standard curve, if we are performing the experiment today, we cannot use this standard curve tomorrow for a new set of the unknown. So everything has to be at the same time range. So during the same lab setting, same day, the machine needs to be calibrated, standard curve needs to be plotted, and then you measure the absorption for unknown using the curve to find the concentration. So we're getting close to 218. Just going to fill up the test tube with the sample B and wait for the time. Okay, 218. 67.3. 67.3%. Okay. Perfect. I'm not supposed to, but I'm going to record these numbers for you in the chat area. So A is 100%. B, you already know what A and B is because you have the table. B, the value for B was 91.7%. Value for C is 85.3%. Value for D (77.3%). Value for E is 74.7%. 74.7%. Unknown A, the value was high. Probably they made concentrated solution, 32.3%. And unknown B, unknown B, 67.3%. Okay, perfect. We are done with the experiment. In order for you to find the concentration, you are going to follow the procedure. Again, if you have any questions, if I was teaching the course, you would ask me. If someone else, another professor teaching the course, you would ask. But at least you have your data. You don't have to be in the lab to collect the data. Since it's the last experiment, I want to wish you all best of luck, and I hope that I was able to help you with the data collection, so remote teaching is going to be possible for pandemic, during this time of pandemic. Thank you, and I'm going to stop the recording.